already did one earlier this time, okay? So let's talk a little bit about apparent weight and planetary motion, and more accurately, apparent weightlessness, okay? So remember, objects orbiting Earth, what force do they feel? Which way does it point?
Down.
Down towards the center of the Earth, okay? So that is a centripetal force. So what are you doing? You're falling, but you're missing, okay? Since you're going sideways, you keep falling, but then because your orbit is like tangential to the Earth, you keep missing hitting the Earth, okay? I think we went over this when we were talking a little bit about orbits earlier, but the feature of orbiting is really you're in free fall. So objects orbiting are constantly in free fall. And actually this is a candle flame if you're in the space station, okay? So why are candle flames shaped the way they are? Well, what does fire need to burn?
Oxygen.
Oxygen, right? So because we have gravity, what happens is heat rises, right? The oxygen comes in at the bottom and then the flame goes up like this. But that's because as the oxygen burns, more oxygen falls and feeds the flame. So you get this shape. If you don't have that, it all just bows out like this. So you have a much weaker flame because it's harder for it to get oxygen. There's no flow, okay? Because oxygen has to kind of sneak in from all sides because it's not dropping as you burn it up, okay? Just a short video of the Veritasium guy getting to go on the vomit comet. Other important thing is the Coriolis Force. So, you know when people tell you like, oh, toilets flush differently in Australia? Well, they do, but that's because they're designed differently. That's not because of the Coriolis Force. Coriolis Force is a large-scale force based on the fact that the Earth rotates, and then we have a rotating coordinate system, which there's a lot of math there, but let me just show you a little picture. Here, this true, this not true. Here's sort of a picture of two things rotating. So wait, does it actually work? There we go. So this is the thing, and this is the actual reference frame. If you fix it so that you're rotating with it, this is what it looks like to you. Okay, since we're on the Earth and it's rotating, we don't see that. What's happening is essentially things at different latitudes move at different speeds, and that causes circular motion when we talk about fluid flow in the atmosphere. Okay, also whirlpools and things that occur in the ocean. But really the Coriolis Force only works for large scale things. Also, you also need to take into account if you're like shooting something really far, okay, like if you have a bullet that will go far enough to experience Coriolis forces, or any kind of trajectory rocket type thing, okay? Last but not least, we have black holes. They are interesting just because they have a much larger density than anything else. So you have a lot of mass, which leads to a lot of gravitational force. The escape velocity for these things, remember this is our escape velocity, tends to be, because the mass is so big, your escape velocity is also going to be really big. And not only is the mass big, because these things are dense, the radius of a black hole is really small, okay, compared to its mass. So essentially, if we had a black hole the size of the sun, it would scale something like this. So same mass, much smaller radius. And the way that you calculate the event horizon, like the point at which nothing, including light, can escape the black hole, is you take that escape velocity, you make the speed of light, and then you solve for the radius instead. Okay, so at that distance from the black hole, nothing escapes, not even light, which doesn't even have mass. Okay, so that's black holes. And that's all we got. We finished gravity.